Bias Point, BJT amplifiers advanced. So welcome back to Bias Point, where circuits come to life one waveform at a time. In part one, we explored the fundamentals of biasing and built up a rock-solid foundation for transistor amplifiers. Now, in this part two, we go deeper into the world of BJT amplifiers, moving from core concepts into real-world performance. This next stage is all about what happens when your amplifier starts talking to the rest of the system. We'll look at AC analysis, gain tuning, loading effects, and the subtle art of emitter bypass capacitors. If part one was about tuning the orchestra, part two is about performing the concert and making sure every signal hits just right. So let's go ahead and dive in. I should have used some kind of musical analogy instead of that one. And let's begin. Millimeter amplifier, foundation of gain. So as we kick off part two of our BJT amplifier series, we return to a familiar and essential configuration, the common emitter amplifier. This is where everything we learned in part one, from biasing to cue point setting, comes into play. In the common emitter amplifier, the input signal is applied to the base and the output is taken from the collector. And the emitter, you ask? Well, it's our common terminal grounded for AC through a bypass capacitor, making it the reference point for both input and output signals. The result is one of the most widely used amplifier types in electronics, known for its high voltage gain and 180-degree phase inversion. So what you put in comes out bigger and flipped. Whether you're designing audio circuits, sensor interfaces, or RF amplifiers, the CE configuration gives you a solid mix of gain, stability, simplicity. But as we explore the rest of part two, real world performance depends on more than just connections. It's about resistance, loading, and the subtle decisions that shape gain and bandwidth. Okay, so I won't go too much into this slide. This is a slide of formulas. What we have there on top is a DC analysis going from left to center. And this section walks through the steps to calculate the operating bias point. In the center there, we have AC analysis from the middle to the right. This section gives formulas for effective output resistance, base resistance. And this slide mainly serves as a quick reference formula sheet for students or engineers working with CE amplifiers. It's ideal for exams, lab work, and design checks. Common collector amplifier, the silent supporter. Now let's talk about a different kind of amplifier, one that's not about boosting voltage, but about strengthening your signal's delivery. Welcome to the common collector amplifier, also known as the emitter follower or voltage follower. In this configuration, the input is applied at the base and the output is taken from the emitter. The collector is common to both, hence the name. So some key characteristics are that the voltage gain is approximately 1, so it doesn't amplify the voltage very much. Current gain is very high, which means it can supply more current to a load without dropping the voltage. And high input resistance, low output resistance. This makes it a perfect buffer stage. It passes the signal along with this little distortion and no phase inversion. So unlike the common emitter amp, there's no phase shift between the input and output. So think of the common collector amp as the team player that doesn't steal the spotlight but makes sure that the signal gets where it's going. Clean, strong, reliable, kind of like, no, I have no sports analogies. Sorry. And collector amplifier grounded strength. So let's take a visual look at how the common collector amplifier is wired and why it behaves the way it does. Again, a little bit of engineering psychology into why an amplifier gets depressed. I'm kidding. That is just an engineering psychology joke. So here the input signal is coupled to the base through the capacitor C sub 1. The output is taken from the emitter through capacitor C2 and delivered to the load resistor RL. Now, pay attention to this key idea for AC analysis. The power supply, which is VCC, is considered AC ground. And why do we do this? Because capacitors block DC, but they pass AC, and the power supply doesn't change with the signal. So that means that the collector is effectively grounded from the signal's point of view. So hence the name common collector. A key takeaway is that the collector remains at a steady voltage, making it a fixed reference for signal variations at the emitter, and the output follows the input. Same shape, nearly the same voltage, but with strong current drive. So this is what makes the common collector amplifier a great buffer. It provides signal integrity, no inversion, low output impedance. It makes it perfect for driving loads without signal loss. The common collector as a buffer. Let's talk about one of the most valuable real world uses of the common collector amplifier, which is a buffer. And here's the problem that it solves. When a circuit with high output resistance tries to drive a low resistance load, the signal can drop or it can distort, and that's called the loading effect. The common collector or the emitter follower solves this beautifully. And why? Well, because it has a very high input resistance, so it draws almost no current from the previous stage. It won't overload or weaken that signal. It has very low output resistance, so it can drive small loads like speakers, sensors, or digital inputs without any distortion or any loss. And remember that there is no voltage gain, and that's okay in this case because the job of the buffer is to preserve the signal voltage while providing current strength. Think of it as that middleman that speaks gently to the sender and boldly to the receiver. Um, the signal shape doesn't change, it just gets stronger where it needs to be. Common Collector, quick reference and design guide. Let's close out our look at the Common Collector amplifier with a fast access reference, right? This is a cheat sheet that every one of you needs to have at hand. And let's start off with the solutions for the DC biasing. When I say solutions, I'm talking about the equations and the tools that you're going to need to solve this. So for DC biasing, the first equation is voltage at the base. It's approximately VEE times the ratio of the voltage divider, R2 divided by R1 plus R2, right? Then voltage at the emitter is going to be equal to voltage at the base plus VBE, voltage base to emitter. Voltage at the emitter resistor is going to be equal to VEE minus VE. And then current through the emitter is going to be equal to VE divided by RE. This is all for the DC biasing. The AC characteristics, again, we're going to look at it with a load and without a load. So with a load, RE is going to be equal to R sub B in parallel with RL. And then without a load, it's going to be R out, which is equal to RS divided by beta on one side in parallel with R sub B. Let's look at the input resistance, or it's the solution for the input resistance. The resistance at the input for the base is going to be beta times R sub E, and the resistance input total would be R1 in parallel with R2 in parallel with Rn at the base. Current gain. So we're going to look at current gain being equal to I sub E over In. Remember that we have a voltage gain of 1. And so overall, what this slide means is you're going to have a high current gain, unity voltage gain, excellent buffering, easy to bias and analyze, and this is your common collector amplifier. It's a voltage follower that quietly empowers your signal chain without distorting it or dragging it down. The common base amplifier, speed and precision. So we've seen the power of the common emitter and the grace of the common collector. Now let's meet the common base amplifier, the CB amplifier. It's less common in basic audio work, but crucial in things that require high frequency applications, especially RF and preamps. The key characteristics of the common base is that voltage gain is strong. It's similar to the common emitter. The current gain is 1 in this case because the input current is nearly equal to the output current. There's low input impedance, so it draws significant current from the signal source. There's high output impedance, which is suited for voltage amplification where current delivery isn't that critical. There's no phase shift with this one, so input and output are in phase. And it's often used in multi-stage design, so typically preceding a common emitter stage to match impedances or handle high frequency signals. And just like its name implies, the base is the common terminal connected to AC ground. The signal flows into the emitter and out the collector. So if the CE amplifier is your all-purpose gain stage and the CC is your buffer stage, well, the CB is your specialist. It's kind of sharp, fast, and perfect for signals that have to move at very high speeds. Base quick guide to high performance. So let's wrap up our look at the common base amplifier with a solid summary. This one-page reference that captures the key formulas and the circuit layout. So our first formula is voltage at the base being approximately VEE divided by R sub 2 divided by R1 plus R2, right? That's just a regular voltage divider. And then we have VE is equal to VB minus VBE. IE is equal to VE over RE, which is Ohm's law. IC approximately equal to IE. Um, and that is it for that part. We can find the voltage across the collector resistor, the voltage at the collector to emitter, and the voltage at the base, right? Let's look at the AC characteristics, right? So the input resistance here, R sub in of the base, is approximately that R prime E. So remember, something very, very low. Output resistance is RC in parallel with RL. The voltage gain, AV, is equal to R sub C divided by R prime E, so it's a strong gain. Current gain is equal to 1. Power gain is equal to the voltage gain. The saturation conditions, here's where the collector current is at saturation. We have the current, the way it shows there on the slide, I sub C saturation is equal to VCC minus 0.02 volts. All this divided by the resistance, like Ohm's law, R sub C plus RE, right? So voltage divided by resistance to give us that saturation current. If we're looking for emitter saturation voltage, so voltage at the emitter at saturation is equal to the collector current at saturation times RE. And so if we want to find the base voltage at saturation, that's going to be equal to V sub E at saturation plus that 0.7 volts. And the takeaway from all this is that this is your slide for the quick reference to help you when you're designing and you're analyzing a common base amplifier, especially in high speed or RF applications where input impedance has to be low and gain must be fast and clean. Darlington pair supercharging BJT performance. So to close out our exploration of BJT amplifiers, let's talk about a configuration that amplifies the amplifier, which is the Darlington pair. A Darlington pair is essentially two transistors connected in series, emitter to base. The output of the first transistor feeds directly into the base of the second, and together they behave like a single super beta transistor. What does all of this actually mean practically? Well, the current gain multiplies. So if each transistor has a gain of 100, the pair provides a gain of up to 10,000, right? So what's available as a single integrated package, so that's to make it much smaller. You can buy it in one chip instead of two individual components. Um, you do have to account for the two diode drops from the base to emitter. So we have to account for the 1.4 volts drop in our equation. You have to account that for when you're biasing a system like this. And then if we look at the circuit, the left half is the classic common emitter amplifier providing voltage gain. The right side, the Darlington pair in a common collector configuration that provides enormous current gain to drive the load. And so here we see the load as a speaker. So think of the Darlington pair as a relay team. The first transistor starts the amplification, and the second one powers it home. It's perfect for situations where you need high input impedance and high current output with minimal footprint, minimal space required. Okay, so now we're going to talk about Cicle pair. Think of it like chicle, like but with a Z, Cicle. This is a smarter beta boost type. It's normally called the complementary feedback pair, complementary Darlington. I don't know anyone who calls it Cicle, but named after the person who invented it or designed it. So just when you thought we were done with transistor pairings, right? There's one more configuration worth knowing. There's several, but the Zicle pair, sorry, again, we call it the complementary Darlington. This setup connects a PNP and an NPN transistor together, as opposed to two NPNs like in the standard Darlington. It still delivers very high current gain, but with an important bonus. it only has one diode drop between base and emitter, not two. So let's go ahead and break this down. For the formulas, if we're looking for IC1 or current at IC1, that's going to be equal to beta DC 1 times the beta current, right? So in other words, DC beta times the beta current. IE2 is going to be equal to the DC beta times IC1. And so overall, you can have the I sub E current um, being equal to the beta DC1 times the beta of DC of the second one times the current at the base, right? So hopefully I said that correctly. The DC beta, the first DC beta and the second DC beta, multiply them together times the current at the base. And what's going to happen is you're going to have less voltage drop. And this is helpful when supply voltage is very limited. You're going to have more thermal stability in some designs. And this works well in the complementary push-pull amplifier stages. So if you want the gain of a Darlington, but a lower turn-on voltage, the Chicle pair, Ziegler pair is your go-to. It's elegant, efficient, and another powerful tool in your analog design kit. Differential amplifiers, the gateway to operational amplifiers. As we close out our series on BJT amplifier configurations, it's only fitting to introduce a powerhouse that combines balance, precision, versatility, and dare I say, a little bit of art and beauty. And this is the differential amplifier, or the diff amp as we call it in the profession, right? So this circuit uses two transistors, typically matched, and it has two inputs. Instead of amplifying a single voltage, it amplifies the difference between two input voltages or two input signals. And that's what makes it differential. And why does this matter? Only the difference between V input 1 and V input 2 gets amplified. So it has a common mode noise that's felt on both lines. That gets rejected. So yeah, so just think about what might be common to both lines. And that's just if noise is being felt by the entire circuit, or you're going to have that noise on both leads, and whatever that noise is, because it's sensed at both leads, gets canceled out. We assume it's going to be noise. Um, yeah. So in the first stage of most operational amplifiers, setting the tone for high precision and stability is necessary. This is going to be ideal for analog signal processing, sensor interlacing, interfacing, and noise tolerant circuits, right? So it'll help reduce that noise quite a bit. Looking at the schematic, we can see that Q1 and Q2, they share a common emitter resistor, R sub E. And so when V input 1 rises and V input 2 falls, current flows more through Q1 and less through Q2, causing opposite voltage swings at the collectors, so V out 1 and V out 2. But the big idea here is that this circuit is all about comparison. It says, I don't care about absolute voltage, I care about which side is stronger. Multi-stage amplifiers, power in progression. So as we wrap up our exploration of BJT amplifiers, let's talk about how to make them truly powerful, not just by design, but by combination. So enter the multi-stage amplifier. A multi-stage amplifier connects the output of one amplifier stage to the input of another, forming this cascade that boosts performance in ways that a single stage cannot. And again, this isn't just an important model for electronics. We use the same model in thermodynamics as well. Um, I'll mention that in a different course. But cascading stages will do that. To increase the overall voltage gain, current gain, or the bandwidth, we can cascade stages, right? To match impedances between different parts of a system, we can use, that's what cascading stages are good for. We use them to filter, to buffer, to amplify in layers, like an audio preamp, maybe feeding a power amp. In the circuit, we can see that we have stage 1 and stage 2. Stage 1, we have Q1, and that's a common emitter amplifier. It's using an NPN transistor. It says right there 2N3904. And in stage 2, Q2 is a PNP amplifier using a 2N3906. It's capacitively coupled via C2. Again, I'm just describing the circuit from everything we've known so far. And the stages are connected or they're directly coupled or capacitor coupled, depending on the design goals. So capacitive coupling, like we see here, blocks DC and allows only AC signals to pass. It's ideal for signal amplification without DC offset interference. And again, the big idea is that multi-stage amplifiers let you stack strengths using different topologies like a common emitter for gain, followed by a common collector for buffering, or even combining Darlington, uh, Z-Clay, and differential designs all into one big powerhouse. And that's it for this slide. I will see you on the last slide. Two-stage voltage gain, how amps stack up. So how do you calculate the total gain of a multi-stage amplifier? Whether you're building a mic preamp, an RF front end, or an op-amp input stage, here's what you need to know, right? Here's the information you need to get. So when cascading amplifiers, the total voltage gain is simply the product of the individual stage gains. So AV total is going to be AV1, whatever AV1 is, times AV2, times AV3, whatever the individual gains are, all the way up to AVN, right, to the nth stage. But engineers, often we use decibels to simplify this. So AV, if we're looking at this now in dB, is going to be equal to the formula 20 times the log of AV. And again, AV in dB is going to be 20 times the log of AV in decimal. Just remember that. And this is important because when you convert to dB, you add the gains instead of multiplying them. So AV total in dB is going to be AV dB1 plus AV dB2 plus AV dB3. So by converting everything to dB, you can just add the dBs and get one big giant total. For power gain, like in the audio systems, we use dB again. So dB is going to be equal to 10 times the log of the power gain in decimal, right? So the number in decibel is going to be equal to 10 times log of the number in decimal. Okay, just make sure I have to enunciate that. And the inverse, right? A is going to be equal to 10 raised to the dB divided by 10. Right? So this is important for audio circuits, radio circuits, signal processing. That was one of my specialties, one of my areas. So that's it. If you're in volts, in other words, if you're in the decimal system, you multiply those gains. If you're in decibels, you add those gains. And the bottom line is whether you're chasing clarity, loudness, or bandwidth, knowing how your stages stack mathematically, that's as important as how they're wired together. All right, I want to thank you very much. This is the end of part 2, and I will see you on the next lecture topic.